Hey everybody, thanks as always for being engaged and doing your best and checking back in. So since we just reviewed trigonometry with right triangles, especially SOHCAHTOA here, um, when it comes to finding missing triangle sides, I want to talk about special right triangles because we can find missing sides of special right triangles without any trigonometry at all because of the relationships that they have. So there are two special right triangles. The first one is an isosceles right triangle. Sometimes you hear this called a 45, 45, 90 degree triangle. So remember from geometry from middle school, whoopsies, an isosceles triangle has two legs that are equal. And remember, the legs are the sides of the triangle that form the right angle. And so in this case, we have two equal lengths called x. You might also see these little line segments there to denote that they are equal. And then since we have two equal sides, two equal legs, we also have two equal angles. And then in this case, they are both 45-degree angles. So that's why we call this a 45, 45, 90 degree as well. So any missing legs here when it comes to an isosceles right triangle is really easy to find. If, for instance, we have the hypotenuse, right? If we have the hypotenuse, or excuse me, we don't have the hypotenuse. If all we have is a leg, we can take the length of the leg and multiply it, right? Multiply it by the square root of 2 to get the hypotenuse. Now, to work in reverse, if, for instance, we have the hypotenuse and we want to find the length of the leg, then all we do is we take the length of the hypotenuse and we divide by the square root of 2. So a couple of examples here to find the missing sides. So in example A, notice we've got those line segments that I mentioned about equal length there. So we're given the hypotenuse and we need to find the legs. So in order to do that, we're going to take the hypotenuse and we're going to divide by the square root of 2. Now, if we think about what that actually is, 7 root 2 divided by the square root of 2, well, we get some lovely canceling there. So it looks like our leg is just 7. And since these two sides are equivalent, we get 7 there as well. We could verify this using the Pythagorean theorem, right, from middle school, just to verify this relationship between 45, 45, 90 triangles. In example B, we're given the two legs, and we know that because they're directly adjacent to the right angle, and so we're trying to find the hypotenuse. Now, to go from a leg to a hypotenuse, we simply multiply by the square root of 2, meaning that our hypotenuse is 5 root 2. And we're not going to try to turn it into a decimal. We're going to leave it in its exact form, which involves the radical. Now, I like example C just because it looks a little bit different. In example C, it's oriented just a little bit differently. And so since we're given the side that's opposite of the 90-degree angle, we are given the hypotenuse, right? Our other missing angle over here would be 45 degrees as well. And so if we're given the hypotenuse and we want to find the length of the legs, remember we take that hypotenuse and we divide by the square root of 2. So we actually get legs of length 8 here. So 45, 45, 90-degree triangles, isosceles right triangles are pretty easy to work with, or nice to work with, I should say. So that's about all there is to that. The other special right triangle we have is a 30, 60, 90 triangle. A 30, 60, 90 right triangle, just like any right triangle, it has two legs and a hypotenuse. So we're going to break these down and I'm going to color code these to label them. The leg opposite the 30-degree angle is called the short leg. So the smallest angle gives us the short leg. And then the leg opposite the 60-degree angle is called the long leg. So we can just refer to them as the short leg and the long leg. And then, of course, we also have the hypotenuse as well. So we can kind of see that in this picture here, right? 30, the opposite of that is our short leg. Opposite of the 60-degree angle is our long leg. And then always opposite the right angle is our hypotenuse. So if I want to find the hypotenuse, I'm going to take the value of the short leg, and if we look at the relationship here, the value of the relationship to get to the hypotenuse is to multiply by 2. X times 2 gives us 2x. So we're going to do the short leg times 2. Now, if I want to find the length of the long leg, I'm going to take the length of the short leg and multiply it by, again, we look at the relationship between x and x root 3, that's multiplying by the square root of 3. And again, we're not going to try to convert that to a decimal. We're going to leave it as an exact value. Now, if I don't have the length of the short leg, I want the length of the short leg, I can use either the hypotenuse or the long leg. If I know the length of the hypotenuse, I'm going to simply work in reverse here, go from the hypotenuse to the short leg by dividing by 2, or I can go from the length of the long leg to the length of the short leg by dividing by the square root of 3. Now, if you notice here, these kind of 4 sets of directions, it's never going between the hypotenuse and the long leg. It just it's obviously possible. I think it's just more of a 2-step calculation. So you might as well get the short leg or use the short leg along the way. So that's why there's no shortcut directly there, because you might as well use the short leg because it's pretty nice to work with. So we're going to do a couple of examples here, and the trick here, it's just a little bit trickier because we have to think about the long leg versus the short leg. So here I've got a 30-degree angle, and across from that is my short leg, right? And this says that the value of my short leg is 3 root 3. And so I need to find the length of the long leg, and I need to find the length of the hypotenuse. So what did we say up above? To find the length of the hypotenuse from the short leg, we're going to take this and we're going to multiply by 2. So 2 times 3 root 3, 2 times 3 gives us 6 root 3 as the length of the hypotenuse. And then if I want to go from the short leg to the long leg, I need to multiply by the square root of 3. And this one just takes a little bit of extra consideration here. So 3 times the square root of 3 times the square root of 3. If you remember from our work with radicals earlier in the year, this is like 3 times the square root of 3 times 3. And 3 times 3 is 9, so this is like 3 times the square root of 9. Well, 3 times the square root of 9, that's 3 times 3, which is 9. So there's just a little bit of extra calculation along the way to make this super precise. But now we've got the length of the long leg is 9, and we've got the length of the hypotenuse is 3 root 3, and that's all we need to do. So we'll take a look at just a couple of other examples here and get some practice in just identifying the long leg, the short leg, and the hypotenuse. So this time we're starting with the same value, 3 root 3, but notice that it is across from the 60-degree angle. So this is the long leg. So highlight that in my green color, make sure I'm consistent. So the long leg is 3 root 3, and I need to find the length of the short leg, and I need to find the length of the hypotenuse. Now remember, it's pretty easy to find the length of the short leg from the long leg, and then it's easy to find the length of the hypotenuse from the short leg. So I might as well kind of take it that route there. So to find the length of the short leg from the length of the long leg, we're going to divide by the square root of 3, and 3 root 3 divided by root 3 is simply 3. So I've got that my short leg has a length of 3 units. And then from there, if I know my short leg, I can find my hypotenuse simply by multiplying by 2, and 2 times 3 is 6. So just knowing those relationships makes it pretty straightforward. There's not a lot of extra calculations along the way. All right, one more example. This time we're shown a 30-degree, we're shown a 10 root 3, but notice that is right across from the 90-degree angle. So this 10 root 3 is our hypotenuse. That means that side N is the short leg and side M is the long leg. Side N is across from the 30-degree angle, so it must be the short leg. So I've got a hypotenuse, of 10 root 3. And as before, it's pretty nice to go back and forth between the hypotenuse and the short leg. All I have to do here is divide by 2. And so if I take 10 root 3 and I divide by 2, I don't know where that came from, whoops, I'm going to get 5. Whoops. Everything's going a little bit crazy. Let's get control here. 5 square root 3, right? I can just take that 10 and divide by 2. So I get my short leg is 5 root 3. Now I can go quickly from the short leg to the long leg by multiplying by the square root of 3. And again, I'm just going to do a little bit of my side work here. So I've got 5 root 3 times root 3, which is 5 times the square root of 3 times 3, which we've already seen before, is 5 times the square root of 9, or 5 times 3, right? The square root of 9 is still 3. 5 times 3 makes this a length of 15. And again, if you are just not sure about these relationships, you can always check your answers using the Pythagorean theorem. There's nothing to stop you there. Remember, a squared plus b squared equals c squared. It's an old friend of ours. So there's no other practice for this. I just wanted to remind us that these relationships exist because we're definitely going to start using these a little bit next week and put some more practice in there. So take care. Thank you for hanging in there, and let me know if you need anything.